All right, so it's very nice to be here. This is my first time at the lab here. I know a number of the researchers who work here, and I spent a year at Lib 6 in 2003, 2004. So I always enjoy coming back to visit Paris and especially to talk about networking with people in Paris. So it's really great to be here today. So I'm going to tell you about work that we've been doing that involves sort of a bit of analysis of the interdomain system, some inference, and I'm going to wrap it all in some very fancy sounding language about complex networks, but really it's about understanding BGP, okay? So this is work with two graduate students at Boston University, Ganja Gerson and Natalie Ruchansky, and also with my colleague, Eva Maria Terzi, who's a professor at Boston University. This is work that has been supported by the National Science Foundation in the US, and we're very appreciative for the support that we've gotten from them. So as you can see, what I'm going to talk about is a distance metric, which I'm calling fine-grained, and it's specifically designed for use in a small world situation. So what do I mean by a small world situation? I'm sure you've heard this term. When we're talking about small worlds, we're talking about graphs that have got low diameter, but not necessarily because they're cliques. They may well only have mostly local structure. And the classic example are social networks, like here's my friend wheel from some time back on Facebook. And the problem that I want to raise on an abstract level is related to the notion of distance in these graphs. We think of small worlds. The interesting property about them is they have small diameter, and so most nodes are close to each other in these graphs. So does that mean, in some sense, that there is no longer any sense of neighborhood? Or can we still define something like a neighborhood in such a graph, even though all the nodes are close? Why are we interested in this problem? So now this is the part where we start to get more practical and talk about a real networking problem. We're interested in this problem for a very specific reason. And so I'm going to explain what the problem was that got us interested in this. Then later after the end of the talk, I'll stop talking about the BGP stuff, and I'll go into more general discussion about this kind of metric and using it in all kinds of situations. But the specific problem that we'll start with today is the problem of routing in between internet domains. You're all familiar with the autonomous system structure of the internet. And here we have a very simple representation. And we'll think of these autonomous systems as nodes in a graph, which is more or less a reasonable approximation, but the differences we'll talk about later. And I want you to put yourself in the mindset of a internet service provider, and you want to know things about your network. A very basic thing you might want to know is what routes go through my network. What paths pass through my network? So here I'm an observer, AS, and I'm interested in knowing, gee, does traffic from this guy to this guy go through me? Does traffic from this guy to this guy go through me, or from this guy to this guy? Now, you can see here that if you knew this structure, you'd be able to answer this question. But it turns out that we don't really know the structure of these paths. So I'll explain why that's the case, but let's just realize that this is an important question. So this would be important if you were interested in, for example, filtering traffic that didn't belong on your network. Traffic that looked, maybe someone spoofs a source address, sends it through your network, and you want to be able to recognize that that traffic doesn't belong on your network. Or you're interested in knowing, from a traffic engineering standpoint, if some traffic were to flow from A to B, would it go through me? What do I need to think about provisioning my network for that? So my example is, if I'm sitting at University of Michigan, or if I'm sitting at a network operator like, let's say, Sprint, and I want to know if someone at Boston University were sent an email to someone at University of Michigan, would it go through my network? Well, actually, Sprint doesn't have a good way of answering that. And the reason is for reasons that you understand because of the way BGP works. Because of the limited distribution of information through the BGP system. So, as you know, the basic action of routing is for an autonomous system to choose a next hop for each destination. And that information is what determines overall routing, but the decisions that are being made are not fully broadcast through the network. They're only sent to essentially a limited set of neighbors. And in particular, an AS sitting here doesn't know, in general, what another AS is choosing as its next hops for, let's say, an arbitrary prefix. Okay? Make sense so far? Pretty basic question. It would be very interesting to know. And unfortunately, don't know. Now, what could we do? Where am I? What could we do? We could observe traffic. So the observer can watch the traffic going through its network, and it could see that a packet went through my network, and it started at I, and it's destined for J, and so, the route from I to J must go through my network. So that's good. But this doesn't fully answer the question, because we only get positive answers to this question from traffic. We don't get negative answers. So the absence, in some sense, the absence of evidence is not evidence of absence. It's a similar problem we have in social networks where you observe interactions between people in a social network, but if there's no interaction between them, does that mean that they don't have a relationship? You don't know. So we're going to treat this as a classification problem. And we're going to be interested in the situation when the observer does not see traffic from I to J. And we're going to ask the question of whether the observer can nonetheless infer that the route from I to J does go through the observer. So that means that if you're watching your traffic and you see 0 traffic flowing from I to J, if this was organized into a traffic matrix, you'd see an entry in your traffic matrix with value 0. This could be a true 0, meaning that the path really doesn't go through me. Or it could be a false 0. The path goes through me, but they're just not talking right now. I just hasn't sent any traffic to J. Good so far? Okay, so let's make this a little bit more formal and turn it into a problem that we can think about from an inference standpoint. So we'll call it the visibility inference problem. There's a ground truth matrix for each observer, and the matrix is organized with sources and destinations. So this 0 means that the path from this source to this destination definitely does not go through the observer. This is the ground truth. On the other hand, the ground truth is not known to the observer. What's known to the observer is measured traffic. What the observer can see is that, in fact, some traffic did flow from this source to this destination, but actually no traffic flowed from this source to this destination. And so our problem then is to take these zeros and label them as true or false. So here we have the false zeros in red because the paths go through the observer, but the traffic isn't observed. If there's no traffic observed, the true zeros are green. And our goal is to label these in a classical detection framework. Timur?
Yes, are sources and destinations, are they routable prefixes?
Mm-hmm. Yeah, so you could think about, in the work we're going to do, the sources are going to be autonomous systems and the destinations will be routable prefixes. But to do this exactly right, you should have actually prefixes on both. But it's a bit of a simplification that we'll adopt today to put 8 S's on the rows.
The question also is, you said that you cannot trust 100% the as prefix, I mean, the BGP base, etc. So the ground truth, how do you build it?
You don't have the ground truth.
We don't have the ground truth.
Right.
Okay.
What we have is this. And if we could figure out the colors for these O's, that would give us the ground truth. We don't have it. So in other words, if we could figure out that these are false zeros, then we would know that in fact this is the ground truth.
The ground truth is really if I sent a packet, would it get to J through me?
Exactly.
Okay.
Exactly. It's an existential question. It's a question about the global state of the BGP system at this instant.
And you build one matrix M per AS or one matrix M per router? Because sometimes you may have flows that do not cross every router in your AS, and so the behavior of your matrix M is not always the same.
Correct. So what we're doing is we're saying, if you observe the traffic at any router in your AS, okay? Then we have, then there's a 1 in this matrix. Okay, so you can see the nature of the dependency. If we have a 1 here, we know we have a 1 here. If we have a 0, we don't know about the 1s. So we're going to take all the zeros in the traffic matrix. We're going to try to label them using a classifier, and our metrics will be among the zeros. What fraction of true zeros do we correctly identify? That's detection, right? And what fraction of false zeros do we incorrectly identify? That's the false alarm rate. And so those two metrics together describe the performance of our classifier. Good? Okay, so far I've told you about the problem and what we can perhaps, our strategy of inference, but why do we think that this problem is even solvable? And the reason is that we have some intuition, and here now you may see some notion of distance creeping back in. You may see why I started to talk about distance at the beginning of the talk. We have some notion that certain destinations may be close to each other, or certain sources may be far from each other, or vice versa. In fact, if you observe the set of routes passing through one autonomous system and the set of routes passing through a nearby autonomous system, you'll see that in many cases there'll be a group of routes that either all pass through this or don't, and all pass through this or don't. In other words, the routes can be grouped in such a way that their behavior is similar at any point in the network. And one way to think about this is the following. If I'm sitting here as the observer and I see traffic from this source to this destination, then maybe it's not a bad guess that even though I don't see traffic to this destination, the route probably goes through me. So what we're going to try to do is take the traffic that we see and use to try to amplify, in some sense, that knowledge. To classify routes, classify zeros of traffic that we don't see. So we're going to take the approach of defining a metric. we're going to need a metric that captures this notion that D1 is somehow close to D2. But S1 is somehow, in that same sense, far away from S2. All right, so far? Good. So, what metric can we use? Well, of course, if you're talking about distance in a graph, you would think I would measure that distance in terms of the number of hops between two vertices. And so let's do that here. We're interested in these two guys. Well, these two are 2 hops apart. So starting here, what are all the nodes that are 2 hops away? Well, this one is also 2 hops away, and this one is also 2 hops away. But these really don't seem to be at all in the same neighborhood of this, the way that this one is. And so we're faced with really the fundamental problem, which is that in graphs like the autonomous system graph, all the nodes are close to each other. You probably know that any typical AS path is usually only 4 or 5 hops long. You don't usually, traffic on the internet doesn't usually go through more than 4 or 5 hops maximum, 4 or 5 autonomous systems maximum, from start to finish. There's exceptions, but I mean that's a 90% kind of rule. So most ASs are close to each other. So this is not going to be a very good metric. Actually, here's measurements to back that up. We have measured a set of prefix pairs, just 1,000 prefix pairs at random, and here's the cumulative distribution of hop distance between them. You can see that 90% of the prefix pairs have a hop distance of 4 or less. So if we were going to take a hop distance of 2, try to define a neighborhood that way, we'd already be encompassing, for any AS, we'd be encompassing 20% of all the ASs in the whole internet, which is just way too big a neighborhood for this to be useful. So we're back to this notion, we need a metric, but it needs to express the idea of routed similarly in the internet. We need a metric which, given 2 prefix pairs, tells me, are these prefix pairs routed similarly? How similarly? With a fairly fine-grained measure. So now I'm going to try to develop that metric, okay? So let's start by just describing it very conceptually, and then I will, later on, give you the specifics that allow us to use it in practice for the AS problem. So, imagine if you could capture the entire routing state of the internet in a matrix. We'll call the matrix H. It's the next hop matrix. Hij is the next hop that I takes going to J. So sitting here in the matrix is the next hop that I takes going to J. So therefore, you can see that any row of this thing is actually the routing table of that autonomous system. Because all the autonomous system does in its routing function is decide the next hop for every destination. So this decision that this blue AS is making is completely captured in one row here. Now, what happens if we look at the columns? What does a column of this represent? For a given destination, the column represents the aggregate set of decisions made by all of the ASs in the internet as to how to get to that destination. So a column represents the decision that this AS chooses this link, this AS chooses this link, this one chooses this link, this one chooses this link, and so forth. So if we're interested in these two ASs, we're really interested in how different the columns are for those two ASs. So let's just use that as a metric. So we'll define something called routing state distance. And routing state distance is simply the number of entries that differ in the columns of A and B. It's the number of times that the set of all the autonomous systems in the internet disagree about how to get to A and B. It's the number of ASs, in fact, that disagree about how to get to A and B. So, well, clearly, it's capturing intuitively what we're looking for, because if it's small, then most ASs think, if you have two prefixes and the distance, the RSD between them is small, then most ASs think they're in the same direction. Most ASs would get to both of those prefixes the same way. It's got a nice property that it's a metric. It obeys the triangle inequality. And you can see that, for example, it does a good job in our test case of distinguishing. For this guy, it does a good job of distinguishing this from this. Here the RSD is 3. Can you see why? Right? The arcs that are different are this one, and this one, and this. Those are the only 3 arcs that are different. Everybody else thinks that those 2 prefixes are in the same direction. Whereas here, there's 5 arcs that are different. There's more disagreement generally in the internet about how to get to these 2 places. Even though they're both only 2 hops apart, RSD says, no, there's a difference between those 2 trips. Okay? Dario, you made me feel like the questions were going to be like pummeling me. So
That's not clear you
I'm
are.
feeling like I may just get out of here without.
Okay, so if you want some questions, I'm sorry. When you say prefix, you're talking about some number of bits in the IP address as opposed to an AS number, right?
Well, let me be specific. What I'm talking about is a routable prefix, something that's advertised into the BGP system as a destination, as a routable prefix.
Okay. And
So the unit is the unit of routing in BGP.
All right.
So here are some toy examples. What's the range of RSD numbers in reality?
It's nice. You can really you can reason about this pretty easily. So RSD, the minimum is 0 for a node compared with itself, and the maximum possible would be the number of nodes in the graph. If every node happened to disagree about how to get to 2 different, then that would be the maximum.
If I have 2 different clients in the same, that are using the same service provider, right, then they don't necessarily have the same result here, right?
It depends whether they're using distinctly visible prefixes.
I mean,
No, that's right. So 2 prefixes can have. That's where it gets. There's some details that need to be clarified here, but 2 prefixes can have a distance of 0 if they're both advertised by the same AS, in other words, by the same provider, right?
okay, so
So-
they don't necessarily have to,
They don't have to.
because the policy could well be different.
Right, especially if, for example, this guy, who's advertising prefixes presumably on both of these, some people may choose to go this way, some may choose to go this way, and so even though these prefixes may be advertised by the same provider, they don't have an RSD of 0 because there's some difference in the internet about how to get to them.
Coming back to the question of teamwork. So does it happen in practice that the RSD is really equal to the number of ASs you have in your graph? Or this is the maximum achievable bound, which is not achieved in practice, practical
Well,
goals.
so that's a very good question, but to answer it, I have to give you more details about how we take this abstract idea and we instantiate it using BGP specifically. Okay, so let's talk about that. So, what nobody really objected to yet was the fact that I said, well, we have the routing state of the internet. Does that present a problem at all?
Well, you already have your answer. Right?
You already had your proof.
Exactly. So if I knew H, I wouldn't be talking to you today. This problem would be solved. I could just look up the answer in H. So clearly, I haven't really done anything yet because I've assumed that we know something. So why is this a useful idea then? The reason it's useful is because of the following. If you think about it, we don't need all of H in order to get a useful metric. In fact, we're only going to need a very small subset of the rows of H. Let me see if I can give you some intuition for why that is the case. Think about this guy. From the standpoint of this AS, everybody's in the same direction, right? This AS never disagrees about any two ASs except for itself. And so it's contributing almost no information to this RSD metric. It's not really distinguishing between things. So in fact, if you think about it, the ASs that really are contributing lots of information to RSD are the ones that have lots of decisions to make. The ones that can go in many different directions, the ones that have high degree. And in fact, we can get most of the information of RSD from a very, very small subset of the ASs that have high degree. So that's the first thing to recognize. We don't need to measure the whole internet. We only need to know about some routing that's being used by the very highest degree nodes.
You have a bound on the degree somehow? As you have degree 3?
The lower bound, what do you mean?
Yeah, lower bound.
So that's not I wish I could be as precise as that, but what we wind up doing is we wind up taking the ASs for which our data tells us that they have the highest degree. So we'd have some threshold we cut off. We don't really know their actual true degree. We only know what we can measure. We can only measure a small subset of all the paths. Okay, so we're now moving from this pure world of RSD defined as an abstract metric onto this messy world of the BGP system. We've only got measurements of certain sets of measurements. We have to do the best we can with what we've got. So it turns out that we can get a small set of rows of H, and it's a very lucky sort of phenomenon that the ones that we tend to measure also happen to be the highest degree nodes. In other words, when we take a set of monitors like the route views monitors, the write monitors, or any other publicly available BGP tables, and we look at the paths that flow out from those monitors, most often those paths pass through these high degree nodes. So we can get information about the routing tables of these high degree nodes by looking at these paths. There's some other caveats which we can go into, but that's probably all we need to say right now. Let me show you what RSD looks like. You've asked this question, and here's the answer. Here's the range of RSD over the same set of prefixes. We have effectively about 250 ASs, or they're really quasi-ASs. I can explain that in detail, but it's just a technical issue. And we find that RSD varies over this whole range. Most of the RSD values are in the middle. But the interesting and valuable thing is that for a large range of RSDs down here, we can define very, very tight, small neighborhoods. So if we go up to a hop distance of 2, we're already at 18%. If we go up to an RSD of 50, we're only at about 1%. So we can draw very tight little balls around these ASs and say, these are the other ASs that are in your neighborhood. Okay. All right, so well, let's use this now. Let's go back to our original problem. And let's see whether we can use this metric to answer the question. So you remember that our goal, what our strategy was we can see a little bit of traffic. And now what we're saying is we can also see a little bit of the routing system. Can we combine those two partial views into an inference method that's effective? So we're going to do this in a fairly straightforward way. We're going to do this about as you would expect. We're going to try to classify each zero in M. So taking a zero ij, we're going to find the set of sources that are close to this source and the destinations that are close to this destination. We're going to take the submatrix that consists of just those sources sending to those destinations. We're going to add up the observed number of entries that have got traffic in them. And we're going to ask whether that's a big enough number. Very simple idea. Look at the sources that are close to this source, look at the destinations that are close to this source, and ask ourselves, do we see a lot of these paths flowing through us via traffic? If we do, then we're going to figure that even though there's no traffic on the path that we're asking a question about, it must be one that goes through us.
So you're not just saying, is there any traffic that goes through? That there's some threshold. You have to. Why is that?
Well, it's for robustness. So if you said if there's any traffic within this submatrix, it would be it would be essentially setting beta to 0, right? And this is just sort of a way of filtering out some noise. You know, the matrices, these traffic existence matrices definitely have a little bit of noise in them, and this process of measuring distance isn't, 100% perfect. And even the intuition that if the source is close to I and the destination is close to J, then the routes are similar. Even that intuition isn't perfect. So all of these, all of those sources of sort of noise we're trying to filter out. Now you notice that there's a couple of magic parameters here, tau and beta, and this is always the thing you need to be very concerned about when you talk about building detectors like this. And I'm not going to go into it, but I can explain it to you if you want, and I can send you a paper that explains it as well. But the bottom line is that actually we can set those things automatically, very easily. It's quite easy to do. So you don't have to tune, you don't have to spend time figuring out what the right tau is or the right beta is. Those things are easy to measure in practice. So what we're going to do then is we're going to look at ASs. And we find empirically that this sort of detector works differently depending on whether the AS is an AS that you think of as being in the core of the internet versus an AS at the edge of the internet. And for the ASs that are at the edge of the internet, it's going to turn out that we're not going to want to use this method. I'll tell you right now. Instead, it actually turns out that these are easier to simply, these are actually, it's an easier problem, but it doesn't lend itself to this metric. It lends itself to something even simpler. So I'll focus then on these core ASs. So what do these mean? This is the 100 ASs that we find closest to the center of the internet by an arbitrary measure. We used the K-shell decomposition. There's the last 100 left as you prune ASs from the edge of the graph, and this is the last 1,000 left. And so that's fine, but how are we going to actually test this? So we're going to test this because we can actually construct small portions of ground truth. We can actually get a little bit of ground truth from BGP data. So if you collect all the active paths, what we did was we collected all the active paths from 38 sources to 135,000 destinations. Now what I want to emphasize here is that means we had every path. Each path from all 38 sources to all 135,000 destinations, okay? So whatever that is, 4 million paths or something. Now why does that allow us to construct ground truth? Because that means if you think about the ground truth matrix, if you think about the subset of the ground truth matrix for just these 38 sources, just those 135,000 destinations, then for any AS in the internet, we know what that ground truth is now. Because we can look into this set of paths. Let's say we wanted to know ij. We could look at the path from I to j and we could say, does it go through this AS or not? If it does, then the ground truth says there's a 1 there. If it doesn't, the ground truth says there's a 0 there. So for us, the bottom line is that for a portion of this matrix, we can construct ground truth from real data. Now, given ground truth, how are we going to simulate the observation of traffic? So what we're going to do is we're going to simply say, well, at any point in time, not all of the sources and not all the sources are sending to all the destinations, so we'll flip some of the ones in the ground truth matrix to 0 as a to create this simulated observed traffic matrix. And we may flip anywhere from 10% or 30% or 50% or even 95%. We could throw away 95% of the information.
Excuse me, but since you're flipping at random, so what may happen right now is that you flip in a destination, but you do not flip in the closest one, so that with your RDS metric you might still have some evidence of traffic going to a close by destination, and so be able to reconstruct the evidence. Whether if you really have erased everything which is closed in the RDS space, then you would get a lot of more hard time in order to reconstruct the...
That's right, and so
when
a
you
fair
flip off
question is
95%, I guess it's you have a hard
you're
time.
doing you're doing it pretty
Okay. So.
yeah. But a fair question is when traffic fails to appear, does it fail to appear randomly, or does it fail to appear in some clustered way associated with sources and destinations? Next question. So we'd love to be able to answer that question from a measurement standpoint. But you're right. Okay. So how well does this do? Here's a picture. It's not really very informative, but in the case of the parts of the matrix where you've got 1s, you can easily infer the false zeros. In the parts of the matrix where you've got 0s, you can easily infer the true zeros. But let's look more quantitatively. I just thought that was a pretty picture, frankly. It doesn't really tell you anything. So, like I said, we're going to measure true positive rate, false positive rate. And what you can see here is the performance of the detector as we vary the beta threshold. And although I said you can tune beta, and you can pick an optimal value of beta automatically, we're varying it just so you can see the trade-off between true and false positives. You can see that, except when you're flipping 95%, when you're flipping, even if 50% of the ones, if 50% of the sources and destinations fail to send traffic to each other, you can still get an extremely high accuracy in both the labeling of true zeros and the labeling of false zeros. So if you were up in this corner right here, that would be perfect. But we're very, very close. You can also see that, and maybe it's not so clear, but the performance is actually, well, it's a little bit better in the Core 100 case. But where it really falls down, and this I mentioned earlier, is that if you were looking at the edge matrices, this method doesn't work very well. And, but I would argue that it's actually, even though this method doesn't work well, the problem itself is actually easier at the edge.
So, in making your decisions, a certain number of the decisions, so even though you don't have the full H matrix, you still have the H that can give you definitive answers for a certain number of cases, right? And what I'm wondering is, you said that you use these metrics to give you the answers. You didn't say that you first answer everything you can using H, and then with the others you do this. And I'm wondering how much of this you can answer using H.
So we discussed in the paper, and I'm going to, the answer is it's kind of involved, but the bottom line is you can't do very much directly at H. What you basically, in order to get a definitive answer, you have to see inside H, you have to see a next hop that tells you that there's a 1 in the particular AS's matrix that you're interested in looking at. That information, the set of AS's that you're looking at is large. These matrices are large. And so that information doesn't fill in very many 1s in these matrices. But it's a fair question. It definitely, there's a few percent that you could do by simply looking up in the table.
But it's small.
It's small.
Does this vary depending upon how long the path is?
That's a good question, and the truth is that we haven't looked at that. You'll notice that what we haven't done is we have not situated. There's 5 players in this, abstractly speaking. There's the I that you're interested in, and the J that you're interested in. There's the observer, and then there's some other I's and some other J's. And what we're doing is we're saying, I'm going to treat these similarly and treat these similarly, and I'm going to assume that they either all go through O or they all don't go through O. What we haven't done, and this is, I think, one way of answering your question, is we haven't asked, oh, well, what if this guy is close here? What if this guy is close here? And what about the length of this path in general? In other words, if these guys are very far apart, then you could imagine routes might have more sort of room in the internet to wander around, and where some of them might go through and some of them might not. Whereas if I and J are very close to each other, then you can sort of infer that, gee, I mean, I'm either on the path or I'm not, and that's true for also the SIs and the SJs. So, does that make sense? So if I'm here, if this is I and J, and SI and SJ, and these guys are close, that's different from if I'm here, and here's I, and here's SI, and and here's J, here's Sj. You could imagine that I might go through J, but Sj might not go through me. So that sort of five-way analysis, it's totally open. We haven't really been able to get down to that level yet.
Yeah.
It's a good, but that's the sort of thing we could do
Yeah.
with this metric. I mean, it's a metric, so you can think of it as a space, and you can think about nodes having a position in this space. In fact, I'm going to talk about that more later on.
Couldn't you do the same thing by clustering the observation of different monitoring points? So since you said the highest number of ops is not that long, you could generalize a little bit the scheme in which you have a single observer to a scheme in which you have a couple or a triplet of observers and look at all the possible realizations. And if in some observer you do see some traffic from ij and s out to sj, then you might infer that the plot goes there, and if you do not observe, you can conclude that it's a true 0 in the one in which you do not observe the traffic.
In general, I think that's what we're trying to do, but I think we may want to talk about that more afterwards, because it sounds like there's more to what you're asking. But in general, that's what we're trying to do, is we're trying to say these guys are, Si and I are close, Sj and J are close, and so if we saw traffic from Si to Sj, then we infer that Ij goes through us.
Yep,
Yes.
but it's not what...
That's not what you're asking?
No. But I might need to draw on a little bit, so probably apply.
Why don't we come back to it? Because I'd like to understand it better. Right. So what does this mean from a practical standpoint? We can get very high true positive rates, very high classification of true zeros, very high classification of false zeros. And the only time that things really fall down, as I said, is when you throw away 95% of the information. You can still do a good job on the true zeros, but the false zeros you start to misclassify. Okay, so since you're all familiar with BGP, let's just say a few more things about BGP before I move on. So these are by way of caveats, essentially. So as you know, the data that you can obtain from publicly observable BGP monitoring points is known to favor the customer-provider links, and it's known to miss the peer-to-peer links. These are latest sort of estimates are that there are many, many more peer-to-peer links than there are customer-provider links, but we miss most of them. However, and this goes back to the point I was making before, if you think about the fact that we've restricted ourselves to this 38 by 135,000 known paths, then the subsets that we're working with, the ground truth subsets we're working with, are in fact known with high confidence. We're not missing information due to this effect. It's simply the case that the portions of the matrices that we're working with are portions that don't tend to have these peer-to-peer links in them. And so it's not clear whether our method would be better or worse on a larger subset of the entire matrix. I actually think it would be better because these peer-to-peer links are at the edge, and the whole problem is much easier at the edge of the network than in the core. Okay, so that's as much as I'll say about BGP right now. Now I'll try and just sort of broaden the picture a little bit and ask ourselves, well, we've got this new metric. It's like a new hammer. What kind of nails can we hit with it? Okay? So let's think about RSD generally. What is RSD like? Let's think about it on some canonical graphs. Well, we can show, it's fairly easy to show that if you were working in a tree, now we have to put paths on these graphs, right? So we're going to use shortest paths. So whenever I say RSD on a graph now, I'll be meaning with respect to the path, the shortest path on the graph. So in a tree, you can see it's a kind of a cute proof that the RSD is one more than the length of the path in the tree. So any two nodes in a tree are separated by a path of length, and the RSD between them is n plus 1. On the other hand, in a clique, the RSD is maximal which is very interesting. Of course, in a clique, the hop distance is minimal, right? Everybody has a distance of 1 from everyone else. But the RSD distance is as large as it can be. Why? Because everybody disagrees on the next hop to everybody. I see the next hop to A as A. Right. Everybody disagrees. Why? Right, because the next hop to, right. I see the next hop to A as A and the next hop to B as B for any two pairs A and B. So RSD is always maximum. And a special case of this tree thing is that in a star, which people like to think about a lot, the RSD is always 3. So let's compare this then to the regular distance metric. So in the regular distance metric, hop distance, the star is, RSD is like the star. In the star, the RSD is like the distance. In the tree, the RSD is like the distance, assuming this is balanced. But in a clique, it's the opposite of the distance in some sense. So what does that mean? Let's look at this famous picture from the Watson-Strogatz paper that was the first to define what a small world was. So we think about a small world. The canonical experiment that Watson-Strogatz did was you take a lattice, you connect the nearest neighbors so that you have a lot of clustering. Everybody's neighbors are connected to each other, and then you randomly rewire a very small fraction of the edges, and you find the small world phenomenon, which is that the distance between nodes drops off extremely rapidly with a small amount of rewiring, whereas the clustering of nodes remains very high. So what would the average RSD do then in this case? It's not monotonic like either of these other metrics. In fact, what happens is that as tree-like structures get built among the paths in the network, when the edges are rewired, they attract many, many paths because they represent shortcuts through the array. So many node pairs start using these edges. And when that happens, then many nodes start agreeing on the next hop toward other nodes. And so that in the small world regime, the RSD becomes small. But as you move out of the small world regime, you get more like a clique. Everybody disagrees. And it's large. And so here's a picture that just tells you that if you have the regular distance metric, this is a cumulative distribution of distances, and the RSD, you see that the RSD maintains its useful range. These scales are exactly the same in all 6 graphs. So D is shrinking as we randomly rewire, but RSD manages to maintain useful range. Okay. Shall we keep going then? Let's look at using RSD to analyze the graph. So let's take a set of 1,000 prefixes in the internet, and let's measure their RSD. 1,000 prefixes, all the pairs, RSD between all the pairs of this. So we have 1,000 by 1,000 matrix. And let's ask ourselves, this is a metric, so let's think of it as a space. These nodes are in some space. What's the dimension of this space? Is it 1,000 dimensional? Is it 100 dimensional? We can answer the question easily by taking the singular value decomposition of that matrix, and we find that the dimension is maybe 3. So that's nice. That means that the metric represents something that we can think of as maybe a 2-dimensional space. So let's just look at ASs in that 2-dimensional space. What do we see? Well, this is a really hard picture to look at. This is just a blow-up of ASs in prefixes in this two-dimensional space. And just for your interest, I've circled, this is a network. This is the Kansas Research Network. This is the Wisconsin Research Network. This is the Iowa. This is a network in Iowa, and this is the University of Iowa. So presumably these prefixes are somehow close to each other in the internet as a result of somehow being close to each other in the real world.
Sorry, what's on the...
Abstract dimensions. So all we've done is we've taken this RSD, this 1,000 by 1,000 matrix, and we used multidimensional scaling, which takes this set of 1,000 by 1,000 distances and tries to find a point arrangement in two-dimensional space that approximately reflects the measurements in this 1,000 by 1,000 matrix. So the distance between here and here is about what it is in the matrix. And the reason that this works, the reason we can be confident, is when we looked at that singular value decomposition, we saw that there was only 2 or 3 large principals. Okay then, this is zooming in. What does the whole internet look like zoomed out? So from looking at all of the 1,000 prefixes, what do we see?
That's it.
That's it. That's the internet. Anything strike you as odd?
What are the 2 parts?
What are the 2 parts? Did you know the internet had 2 parts?
Wait, is there the ocean between somewhere?
Sorry?
No, I mean, this is not matrix space in which there is latency, so it cannot be ocean, but so why is this...
I mean, these points in this picture are, the distances between them are approximately RSD.
RSD, yeah.
And you can, this is just a sample of 1,000 prefixes, but these prefixes were sampled randomly. You can sample as many times as you want. You'll always see that the cluster, that the points break down into a cluster of about 75% and 25%. Anybody want to take a guess?
North America and the rest of the world.
That was the first thing. I was like sure that this had something to do with geography. It has nothing to do with geography.
Academics versus rest of the world?
Then I thought it must have something to do with providers. It must have be academic and commercial. Nothing to do with that.
Is it a cluster in the core?
It's not in the core. It's not the case that this is the core and that's not, or vice versa. So, I stared at this for a long time, and I have to show you, this is what I felt like I was staring at after a while. This is the Greater and Lesser Magellanic Clouds, and I had about as much clue about this picture as I did about this one. So, you know, we do have the data. We can, in fact, inspect what's going on, and if you dig in far enough, you finally find out what's going on. So I'll explain to you what's going on. First of all, let's just reason about it a little bit. So what is RSD? RSD is saying that there are, that the distance tells you how many ASs disagree about the next hop between these pairs. So for these 2 points, most ASs agree on the next hops. For these 2 points, most ASs disagree on the next 2 hops, right? But for these 2 points, they agree. So that means that these guys are mostly in agreement, these guys are mostly in agreement, but they're both in disagreement, so that must mean the disagreements are the same. Does that make sense? The disagreements are the same, and that's the key to understanding this. What this represents is a coordinated routing decision made by many different ASs. Independently, for their own purposes, they're making the same set of decisions. Let's think for a minute about how the AS works. Normally, the internet works. Normally, we think of routing decisions made independently. Each AS has its own set of criteria that it uses to decide how to get which next hops to choose for any given prefix. So to get to a prefix, you would typically go through, let's say, a top-level AS. And all of the prefixes that you can reach from a top-level AS, you can reach all of these guys from this one, and then you can reach all of these, we would say are in that AS's customer cone. They're all the ASs that you can reach by following provider to customer links. Now, normally, that doesn't mean you're going to use this AS for these guys, because they've got many other ways to be gotten to. And you have a typical top-level AS has a huge customer cone. It could be a large fraction of the internet. But you don't get to the large fraction of the internet through that AS. You make different decisions for each of these prefixes. For each of these prefixes you make. Okay? Unless, and here's the kicker, unless there's one AS that everybody always prefers to get to any of its customers. And if that were the case, then many different ASs would make the same decision. They would choose this AS for any of its customers. Does that make sense? And that would lead to a picture like this, right? And that's exactly what happened. So it turns out that a large fraction of the ASs in the internet are all following this same rule. Independently chosen. They all came up with the same rule. And the rule is that there's one special AS in the internet. And these guys are all following the rule that I'm always going to use ASX to get to any customer that's in its cone. It's just a great AS to use. And when you look at the ASs that are making this coordinated decision, they're not related in any obvious way. So we, like I said, we dug into the data. Some of the ASs that are all making the same decision, I've got it written here. One is a Russian provider in St. Petersburg, one is a Swiss provider in Zurich, another one's a Canadian provider in Quebec. All making the same decision. And the decision is, if I can get to a prefix like this, that's in the customer cone of this AS, I will always use that AS to get ASX to get it. And so which prefixes are in the customer cone of ASX? These.
Are you saying that there are two kind of highly influential ASs, X and Y, or are you just saying that there's
I'm saying
one
there's
X?
X and then there's the rest.
There's X and the rest.
Nobody wants to know what X is?
Of course.
It's an AS called Hurricane Electric. And it's known for providing very inexpensive connectivity. And what this is showing us is that is an economic decision, a coordinated economic decision being made by many ASs throughout the internet, which is that if I can ever get to a prefix through Hurricane Electric, I'm going to use them because they're cheap. And so here is a typical example. This is some arbitrary prefix in the internet. This is the set of all BGP paths leading to it. And here's Hurricane Electric. So there's, again, a set of ASs that are always saying, look, if I can get to somebody through Hurricane Electric, I'm going to go there. The rest of the world says, oh, I might use this AS to get there, I might use that AS to get there, I might use that AS to get there, I might use that AS to get there. Any questions?
Hurricane Electric might be wonderful, but why aren't there sort of many constellations?
There probably are. In fact, a great question is, is there deeper structure in here? Or is there deeper structure in here? Is there some, there are other economic decisions that we can tease out of this thing as observable coordinated decisions. And maybe, you know, maybe there's, if you think about these guys and these guys, you have almost the same situation. There's some decisions that are being made the same here and the same and differently here, but different in the same way. So there's definitely room for more of this analysis. Any other questions?
In this strange space,
Yes.
so the first metric, which is the most important, takes a wider span, and it is later contained. Whereas in the other case, it seems like more that both coordinates are counting. So, is there any? I mean,
Which one? The other picture?
No, in this one. I mean, the blue one is like
Yeah, there's more continuous variation.
yeah, and it's narrow. And whereas the red one is a ball. So, is there any sense behind that, or?
That's where that's. I mean, what I would guess is that there is some more coordinated decision making going on that describes this dimension. It says these guys are the same in a way that they're all different from these guys in the same way, which forces them apart in this space. Now, there's many ASs that all differ in the same way in their decision. Yeah.
Do we have any thought about how we might know why? Why is it that not everyone is making this decision? Is it because of where they're situated, or is it because there's some trade-off? Hurricane Electric is cheap, but maybe
Maybe the performance isn't that good.
right.
That's a really good question, because if you look at the ASs that I mentioned that are making this coordinated decision, you might imagine, like, let me mention them again: a Russian provider in St. Petersburg, a Swiss provider in Zurich, Canadian provider in Quebec, another Russian provider that spans Europe, and another Swiss provider. Those are 5 of the examples we came up with. These could be all very, let's say, small scale ISPs, which may be economically forced to make a decision purely based on price. And so this could reflect a sort of, if we could tease that out a bit, it would be interesting to see if that reflects a sort of a price versus performance issue, where what pushes these guys over here are the pure price decisions made by a small set.
You could even try and make some sort of quality, quality measurements, and see if things differ.
Huh. You could. Yeah, we could use looking glass servers to measure packet loss, something like that. Okay, so these are my collaborators, Gonja Gerson and Natalie Ruchansky, who are, like I said, graduate students who get Terzi as a professor in BU in the data mining area. Any other questions? Yeah.
In your approach, you never consider AS business agreement, and so I fear that you may infer wrong path in terms of AS relationships. Is what I mean?
No, I don't think we are. The reason is we're not inferring any paths at all. We're simply measuring paths. We're taking paths that are observed from the BGP system. So, and these are active paths, meaning these are not backup paths or paths that aren't in use. These are paths that are actively being used to move traffic. So, right. So they reflect what's really going on out there. All the paths that we used in the RSD computation.
But if I'm not wrong, you infer some coefficient in your matrix H that are deduced from observed paths.
Right.
And so what does guarantee that The coefficients you are filling are right.
So, is this the, are we going back to this picture? I think I see your point here, which is that just because these sources are close to this one, these destinations are close to this one, we don't know that the sources go through, right? Well, we're only using observed traffic between these two. So the only time that we infer that these go through is when we actually see traffic. So again, it must be the case that they do because we're actually seeing the traffic from it.
And maybe, I don't know if you have done this job, but maybe you can compare your inferred paths with inferred relationship and see if this pattern remains valid. Maybe.
Right. That's true. That's true.
Because you
Yeah,
only
that's
know
right.
to compute valid paths, you only need to do a graph transformation, which is very easy to ensure that every path you compute remains valid. So maybe in the last picture, when you see your two groups of nodes, maybe you will distinguish more easily every tier 1 AS, for instance.
Oh, here you mean.
Yes. Because I believe, I'm not sure, but I think that maybe some results are a little bit biased due to these constraints that you do not take into account.
I don't see, maybe we can discuss it more after, because I don't really see how the customer-provider relationships play into this H matrix. But I agree with you that when we're inferring visibility, the aggregate visibility that you infer implies some paths.
Mm-hmm.
And we don't check to see if those paths are valley-free customer-provider paths. And that's what we're doing. Anything else? Yes.
Do all the tier 1s appear
Together? No. No, there's no tier separation in this. Because some of the tier 1s are accessible through other tier 1s. So, for example, a provider in St. Petersburg will choose Hurricane Electric as its provider to get to, say, Sprint. That makes Sprint, put Sprint over here. Yeah, that's a good question. I don't know. I don't know if tier 1s would be over here.
A question about the metric. You have a slide in which you compare the op distance between ASs and the RSD. So, and you also have shown some example for different topologies, which were some cases in which you highlight very well some differences, for instance, for the click and etc. But what I'm asking is whether here, roughly, the order of the metric is the same, but just the RSD metric gives you more granularity. So what you're better have to do is to distinguish guys that are at distance 2, or 2 and 3.
We asked that
more
question.
distances.
I don't have the plot here, but it's not really, they're not correlated strongly.
Okay, they're not
correlated.
No. But
If you plot a scatter plot, it's just a big round plot.
I guess that far away guys are far away in box metric spaces, right? So if a guy is distant in up count, is also distant in RSD.
We didn't really see that, but now I wish I had the plot. I can look that up, but I don't. We didn't even really see that the largest hop distance pairs were also hard RSD.
Because you said in the figure that most likely a source destination pair will be far away, most likely the RSD will grow.
If
But there are different, I mean,
if these are far away,
yeah.
then I will be far from J and RSD. But you notice that we're not actually using that information right now. That's kind of, you know, unexplored information that we could imagine trying to use. But right now, we're not using the fact that I has got some distance from J in RSD space. We're simply finding some SIs that are close to I, finding some SJs that are close to J, and
So you said that RSD is good also for clustering close neighbors.
yeah.
Kind of.
Yeah, so clustering would be but I mean, in some sense, so clustering would be a smart thing to do, especially now that you've seen the last few slides in the talk. And we didn't really do clustering, but if you look at what we did do, it's not, it's got some notion of clustering, it's got some notion of nearby nodes. What would be smarter, though, would be to say, you know, instead of a fixed tau, do some clustering that allows different clusters to have different sizes. That would be probably a little bit more precise.
And I mean, in your guess, do you think that RSD might be a good tool, ever, as you say, to kind of generalize the routing state of the internet with a very small size of information?
Yeah, that's exactly what I think. I think that RSD is an incredibly useful tool for talking about the routing state of the network. So, and my sort of existence proof for that statement is that previously people have talked about something like this. There's this notion of BGP atoms, okay? And what that is, our people recognized long ago, 10 years ago, that there are pairs of prefixes that are routed the same everywhere in the internet. Okay? And they said, you know, if we're going to do prefix-based analysis of the internet, we don't need to analyze every prefix. We can just put the prefixes together into atoms and analyze those, because everywhere you look in the internet, the prefixes in one atom are routed the same. So you think about two prefixes that are announced by the same provider, and their prefixes are not multi-homed. So they're really coming into the internet the same way, exactly the same way. Everybody in the internet probably makes the same decision how to get to them. So those are what you think of as atoms. Well, RSD is just a generalization of that. It's instead of saying distance 0, I'm going to say I can have a distance of that's slightly more than 0. I don't have to have this prefix routed the same everywhere. Maybe it's routed the same way in all but one of the locations of the internet, or all but two of the locations. And that's exactly what RSD is.
And could it be as like small RSD, as in like double tree or the inter, at the edge? That's, I mean, it's more likely that two close aliases are connected. And
well, two things you could do. One is you could put prefixes together. So RSD would be a very interesting tool to think about for use in something like DoubleTree, right? Because that problem is all about reducing the number of measurements by seeing that once you've got a measurement to some location, if the other measurement meets it, you don't need to measure the rest of the way. Well, if the two locations are close in RSD space, maybe you can even guess something about the measurements. Now, the other thing you could do is, and I got no idea how you would actually do this in practice, but it would be fun to think about, would be try to apply RSD at the level of routers. And that's just mind-boggling, so I won't try to. But it's certainly, abstractly, it's easy. You can conceive of applying it at that level as well. Sorry.
Excuse me, in the definition of SI and DI, instead of we consider if RSD is smaller than a constant, can we choose, for example, the k smallest RSDs? Because if we fix a constant, it is possible that in different parts of the graph, this constant may be different. So if
Yes.
we choose the k smallest, maybe it is great.
That makes a lot of sense, and we didn't do it. But that's a very good point. I mean, absolutely. Sort of a nearest neighbor.
Yes.
In fact, we think of this as a nearest neighbor. We think of this, like I said, the other professor I work with is a data mining person. And so, in our discussions, we often talk about this as nearest neighbor estimate. So we're sort of taking nearest neighbors in this RSD space, but we used tau, we could have used k nearest neighbors, and that would have been an interesting comparison.
Yes.
Yeah.
In this way, the beta constant is also easier to decide because if the k is already decided, the size of Si and the size of Di.
That's a good point too. I agree. Sounds like you're halfway towards another paper on this topic, so I'm glad to hear that. Those are very good suggestions, and I can't tell you why we didn't do it, except that we just didn't do it. Dario?
Otherwise, I wanted to have a comment. So since you said that RSD now is a metric,
Yeah.
so does knowing the fact that I prime and J prime are close to I and J give you some information, whether you know what is RSD IJ to get to RSD I prime J prime. So does this knowledge of having something close to the expression pointed
So maybe I could, is it fair to say that you're asking me if I know some elements of the RSD matrix, this is the I's and the J's, and this is RSD in here, that I could guess some of the others?
Yeah.
Yeah, I think that's true. I think that's true. Why do I think that's true? Because I measured this matrix, and I saw that the effective rank was only about 3. Okay? So that means that this can, in theory, this can be factored into 2 matrices that are n by 3 and 3 by n, fairly accurately, right? But this is only 3n, or 6n values, and this is n squared. So in principle, you probably only need some thing like, rank times n observed values in here in order to guess the rest. So this topic, matrix completion is called, it's called matrix completion typically. You can observe some portions of the matrix and you want to infer the rest, and you make some assumption like the matrix is low rank. So I definitely think you could, if you could observe some RSDs, you could infer the rest. Any other half-written research papers? These are great suggestions. I mean, really, very good suggestions.
So I think we can. So if there is not any other suggestion, 1 hour and 20.
Okay, all right, you're right. 1 hour 20 is actually,
So I think we can thank the speakers.